So far we've talked about charges, often protons and electrons, and then we talked about how things become charged, and now we're going to talk about electric forces. If you recall, a force causes a change in motion. Okay, so let's go ahead and look at this simulation here. Okay, these balloons are at rest. Now we learned before, and they'll stay at rest. I'm going to leave the yellow one over there. But before we can charge it by friction. Okay, now this balloon is charged. If I let it go, it's not going to stay at rest. The neutral one stays wherever I put it. Okay, but this charged balloon no longer stays that way, and that's because it is attracted to the net positive charge in the sweater. Okay, so from this we learn a little bit. One, that there's a force that's causing this motion, okay, and we call it the electric force. And two, that it was attracted to the opposite. So opposite charges attract. So if something's got a net positive charge and something else has a net negative charge, they're going to be attracted to each other. And you're going to see like charges repel. So let's take a look at that. So I've charged up this balloon a little bit, and I'll put it down there. Go over and charge up this balloon. Okay. Now if I put the yellow balloon right next to the green balloon, they're both negatively charged. Look how the yellow balloon goes away from it. Okay. It leaves and goes away. And you notice now it's sticking to the wall. Remember, that's because the wall will become polarized. It's neutral overall, same number of positive and negatives, but it becomes polarized, and then it gets to be attracted over here. Okay, so we've got like charges repel. Okay, so both positive repel, both negative repel, and opposite charges attract. Okay, and we call this force that causes the motion the electric force. We use the symbol F with the subscript electric. And we're going to go ahead and abbreviate a little bit more with just an E for electric. Okay. The units are going to be newtons. Now, in order to get the units to be newtons in our equation, we need to use coulombs for the unit for charge. So we need to have Q being coulombs. And what you're going to notice is that a lot of times in the problems, it will say 6 millicoulombs, and we need to convert that to coulombs before we can substitute it into the equation. So we know millimeter, okay, we've seen the prefix milli before, and it means 1,000th of a coulomb, or 10 to the negative third coulombs, okay. Then the other one that we'll need to know is a microcoulomb, okay. A microcoulomb is 10 to the negative sixth, and then the last one that we're going to know is nanocoulomb, and that's 10 to the negative ninth. You should be familiar with millicoulombs, so that one shouldn't be too hard to memorize. And if you look at this, nano is to the negative ninth, so nano 9, and then just remember micro is the one that's in between the two at negative 6. Okay, so we want to use newtons, which means we need to be in coulombs, so we need to know some metric prefixes, because oftentimes the problems will have them listed in milli, micro, or nano. And then we've got our equation. So the electric force is equal to K, which is a constant, times the charge in the first object, times the charge in the second object, divided by R squared. And R is not a radius, it's the distance between the charges. Okay, so to be a little bit careful there. Now, if we look at this equation, it might remind you a little bit of the gravitational equation, where we had a constant g times the two masses divided by the distance between them squared. And this is what led Einstein to believe that there should be a unifying theory of everything. Okay, so it kind of leads to that we get these equations that are very similar, okay, for different things. So based on this formula, you're going to see that the closer the two charges are, you can divide by a smaller number, so you're going to get a greater force. The further away they are, you're going to get a smaller force because you're dividing by a bigger number. Okay. Another thing to take note of is that the electric force is a vector, which means it includes a direction. So you're going to say they are attracted or they are repelled. So you might find the electric force between these two charges, and then you just say, give it a direction. Well, it depends which one you're talking about. If you're talking about the force on charge A, then the direction is going to be to the right. If you're talking about the force on charge B, the direction is going to be to the left. So you have to know which charge you're talking about as well. But it is a vector, and we need to take that in consideration. We need to know which charge we're being asked the force is coming from. Something else that we'll pick up later with is, let's say there's more than two charges. So you've got a positive and a negative, and then we're going to go ahead and talk like we're looking at charge A. We're going to put a third charge in here, okay, charge C, and we'll make that positive, okay. So A is going to be attracted to B and repelled from C, so A is going to want to move to the right and up. So the overall charge is going to be the vector sum of the two. So we'd have to find the vector sum, which we've done before back in previous chapters.